Electrochemistry is the study of relationships between electricity and chemical reactions. In a redox reaction, something is giving up electrons while something else takes them. And a simple example is the reaction of zinc metal with hydrochloric acid, which is a source of H+. In the reaction, when you put the zinc metal in solution, it heats up rather quickly and it begins to froth and boil because it's a vigorous reaction, and in the end what you produce is zinc ions in solution and a lot of hydrogen gas. The important thing to observe here, though, is that the zinc metal, which starts off with an oxidation state of 0, ends up giving up electrons. All metals give up electrons. By definition, a metal is something that gives up electrons. At least a part of the definition. An element is not metallic if it doesn't give up electrons. And you see what happens to the zinc. From a 0 oxidation state, it becomes positively charged. It's given up 2 electrons. What happens to the hydrogen? It starts off at a +1 oxidation state, and it ends up at 0 in the form of hydrogen gas. So the hydrogen has taken the electrons that the zinc has given up. A good way of remembering the rules of reduction and oxidation is to say, use the mnemonic Leo says Ger. Loss of electrons is oxidation, gain of electrons is reduction. On the next board we see another example where sodium metal gives up an electron to become a sodium cation. Bromine liquid, bromine is a brown viscous liquid. If you were to put sodium in liquid bromine, what would happen is this. The bromine would take electrons from the sodium to become bromide. The sodium would give up electrons to become the sodium cation. The two would then become attracted because of the electrostatic attraction between them, and they would form a compound of sodium bromide, as we see summarized here. In a redox reaction, an oxidation is coupled with a reduction. One substance gives the electrons while the other takes it. Sorry, I wrote the wrong word here. In the example above, twice the first reaction coupled to the second reaction would constitute a balanced redox reaction. And we have it summarized here. We see the sodium metal reacting with bromine liquid. 2 electrons are appearing because the sodium is giving them up, and 2 electrons are appearing on this side because the bromine is accepting them. Once we balance the equation, the electrons that appear on both sides are cancelled, and the net equation is that sodium combines with bromine to give you sodium bromide. The technique for balancing redox reactions is called the half reaction method. It's the one I'm partial to. Is to divide the equations into 2 half reactions. Secondly, to balance each part of both equations by A, balancing the elements, B, balancing oxygen by adding water, balance the hydrogen with H+. If the reaction is taking place in acidic solution, you have H+ ions floating around. And secondly, and lastly, balance the charges with electrons. We have an example of it right here. The last couple steps is to also multiply the half reactions with integers to create the same number of electrons in each half reaction, and then we add the half reactions, cancel species appearing on both sides, and then just double check to make sure everything is balanced. The example here, we show the dichromate anion reacting with iodide to form chromic and iodine. In the first step, what we did is we separated the 2 half reactions, so that we had chromium and, I'll show you what it looked like before we balanced it. We had the chromate anion turning into chromic. Chromium balances. The next thing is to balance the oxygen, so we had 7 waters on this side to balance the oxygens. Then we have to balance the 14 hydrogens that appear here by putting 14 hydrogens over here. Then we have to worry about balancing the charges. We have a net charge of +12 here and a net charge of +6 here, so the way to balance that is to add 6 electrons. On the second half reaction, we simply add 6 electrons on this side because there are no oxygens or hydrogens to worry about. Once we add the 2 half reactions, the electrons cancel, and this is the net equation that results. And you can throw in the states of all the various species that are in solution at the end. Usually save it for the end because it tends to clutter the calculation. This would be taking place in acidic solution. And one last point I'd like to add is that each half reaction comes with a voltage. And when you add the 2 half reactions, the 2 voltages are added. It doesn't matter whether you've multiplied the reaction by 2 or 3 to make the electron balance. The voltages aren't multiplied. They're simply added as they've stated. So this reaction would have a net voltage of 0.79.